Yo, I am just waiting to confirm that this is working. Hold on one sec. I'm using a new streaming platform this time. So let me just make sure. All right, I am live. Awesome. Okay. I'm just exploring this new streaming platform. Okay, I'm not going to be able to see the chat because I would need to log in and I haven't set that up. So next time I will be looking at the chat, but this time, honestly, every single time I'm doing these streams, I'm just trying to do one part better or at least experiment with something, learn from the last one, try different things, see what works. I think it's actually quite difficult to do streaming is harder than it looks. I mean, I never thought it was going to be that easy, but um, it's hard to like set up everything, coordinate everything, do all the things that I wanted to do, and also talk for an extended period of time. So far, each stream has been about an hour, and I'll probably continue doing that. I want to eventually have guests. I want to have more interesting content. I tried preparing a little bit more this time relative to last time. And so I'm going to be able to do some illustrations to show the points that I'm going to make. And a lot of this stuff is going to be just off the cuff. I'm hoping to get that balance where I have some preparation but also a lot of spontaneity. And so last time we were diving into this talk by Andrej Karpathy called Building the Software 2.0 Stack. If you can see, it's up here in this playlist. And I want to continue going through this video, but I thought that there's a lot of prerequisites to fully understanding what he's talking about. And I thought it would be very interesting if we could go and learn a little bit more about AI. And I'm no AI expert, but I do know some of the basics. And I have learned some really cool stuff I'd like to share. And so this video here that I want to react to, I'm going to react to this first. This will give a primer of the background that I think is necessary in order to really appreciate what is in this video by Andrej Karpathy. And then after, so we'll go through this. I will talk about a few concepts, and then we're going to jump back into this video. And I don't think the last stream was very good. I wasn't prepared. I hadn't thought about some of these things for a while, so I was a little bit rusty. And also, we were testing this audience participation mode in the stream, and it was glitchy. So my friend kept trying to call in, and it distracted me. So we would have technical issues all the time. And so I don't even recommend going back and like watching the last stream. It wasn't that good. This one I hope is going to be better. And I don't think there's going to be any technical issues, although we are testing out a new platform. So just bear with me. I'm going to get better at this. And yeah, so let's dive in. And I'm going to go and give a recap of this after we watch this video, and then we will try to finish reviewing what Andrej Karpathy is talking about. And at the end, if there's time, I'm going to tie that into crypto and talk about what the lessons from AI are for crypto and how AI and crypto are deeply intertwined. I may not have time for that this time, so we'll see. That might be a part 3 to this series, but treat this as a part 1. Just start watching here, and if this is bad, then I'll make another a part 3, and that'll be the new part 1, and I'll recap everything from this one, and yeah, and eventually there'll be something that people will want to watch. So, okay, let's get started. I'm gonna just play this video. So this video is gonna talk about how this is the best video describing neural networks that I've ever seen, and it doesn't go too much into the technical details, which there's a lot of great videos that do, like by what's that guy, 3 blue 1 brown, or 3 brown 1 blue, 3 blue 1 brown. This guy, he makes great videos. There's so many people who make great videos that visualize this and explain every step of the math. But what I want to do with this series of streams anyway is not go too deeply into the weeds of exactly what is the code doing here and there, and I don't want to get too technical. I want to stay at a high level. So, but this is a great video. So just like if you're watching this, maybe take note of this and come back to it because this is just so good. And if you do go on my YouTube channel, which is youtube.com/ LZRS CG. If you're probably watching this on X right now, so it's just my Twitter handle on YouTube. I have this sources playlist, so everything that I talk about is added to this, so you'll never lose it. So just you can save this or follow this account and look at this playlist. Okay, so without further ado, let's get in and let's see this amazing just high-level description of what is going on with deep learning.
AI, where
1 second, let me actually make this full now. And not only is this going to be full screen, I'm going to put on some captions so that you guys can, if you're watching, you can understand it better. Okay, let's
so far in this series, we've looked at how deep learning was a paradigm shift in AI, where intelligence is understood to be the ability to learn instead of following human instructions. The problem is
just so you know, this is an existing YouTube series by this guy, Art of the Problem. I haven't watched the other videos, so I cannot vouch for how good the other ones are. But if I were to guess how good the other videos are, I would guess they're pretty good because this guy is good. I see that the video is kind of cut off on the screen here, so let me just resize this for you guys so that you can see the full thing. But don't worry about the previous videos. This is a standalone video. It speaks for itself.
people see neural networks as some kind of magic. It's not clear why they work. And so in this video, we'll explore the guts of a neural network. Recall that a neural network receives an input, which we could call a perception. This could represent an image, sound, text, anything we want a network to perceive. A perception boils down to a list of measurements that are provided as input as a list or vector of values. For example, if it was an image, each value would represent a single pixel's value in that image.
Okay, so just really quick, I'm just going to break this down. I mean, this is pretty simple, but if your perception, like literally perception from the standpoint of a person, you are sensing things. There's incoming data coming into you. And we can think of a neural network having a similar situation where there is data that's being fed into the neural network. So if this was image recognition, as an example, there would be, let's say, this image of a dog as an example that he chose. So if you wanted to have an AI that classifies this as a dog, you would feed in this image, which would be a list of colors, essentially. So each pixel on the screen would essentially would either be one color at each pixel. And somehow through this list of colors, you would have to deduce that this is a picture of a dog. And this is the type of a thing that a neural network can do. So if you kind of look at this
input,
you see how he's framing this. This is a neural network. And we're going to get into what the different layers are. And these are each neurons in the network, and these are the connections. I forget what you call those things. But the point is you input a list of numbers, which are colors and numbers can be mapped to each other. And this list of numbers then is going to somehow do something here, which we're going to talk about. It's going to do something inside of the neural network, and then at the end, you're going to get a result. So he's going to walk through this. I just wanted to make sure, just in case anyone didn't understand what he's saying, that's what he's saying.
But as a list or vector of values. For example, if it was an image, each value would represent a single pixel's value in that image. And these values are represented as electrical pulses, which are sent to the first layer of neurons, which we call the input layer. And based on these values, some of the neurons in this layer will fire in a predictable manner and send off a pulse to the next layer of neurons, and this process repeats, creating a wave of electrical activity that passes through all the layers in the network. At the final output layer, certain neurons turn on or off. The output can describe the degree of belief that the input is or isn't some concept it's been trained to recognize.
Okay, so in this very simple example, this is a dog-cat classifier. So you're going to either have an image that has a dog, or it either has a dog or a cat, and you're going to feed this dog or cat image into this neural network. And then at the end, you want the neural network to tell you, is it a dog or is it a cat? And so essentially, think about these things as almost like a switch that can be on or off. And again, we're not going into the details of all of this, but um, there are multiple layers of these that get activated according to some sort of logic. And the input from this layer goes into the next layer and so on. And through activating each layer, somehow, we'll get into what is happening conceptually, but somehow by the end of it, assuming that there's a cat, assuming that these numbers were the numbers that encoded an image of a cat that was fed into the model, at the end of it, this is going to be what's highlighted. The cat is going to be what's highlighted, and so that would mean that we showed an image of a cat, or at least it would have predicted that this image was a cat. And so you think, okay, that's interesting. Okay, you can just tell if something's a dog or a cat, but this is a very powerful concept. So, like for example, with a large language model, you could predict the next word. So instead of just choosing between the words dog and cat, you could be choosing through almost any, what all these different tokens that represent different words or segments of words. And if you're just trying to predict the next one and you continuously in a loop, you could imagine how you could generate a bunch of text. And we'll get into language models right now, but what you have to realize is it's essentially a classification. It's essentially a classifier. You're putting in the existing text into something like ChatGPT, and then the next word, so to speak, is what it is predicting. Whereas in this case, we're talking about you feeding in an image and it's just saying, is it a dog or it's a cat? But what's really cool about these simple examples is, although it sounds like a dumb use case, it's simple enough to understand what's happening, and you can actually see the cool stuff that goes on when we do it. So let's keep watching.
Based on the activation level of the output neurons. A key question is, how does a neural network connect perceptions to concepts? Put another way, if we freeze a neural network as it's processing the picture of a dog, what is it doing inside right before it knows it's a dog? Let's start with the simplest possible neural network, a single neuron with just one input and one output. You can think of a neuron as a switch. The input is represented as a number, which is the value of something being measured, such as the temperature outside. If the input value is above a certain threshold, what we call the activation threshold, it flips the output on, otherwise the output remains off. And to better understand the guts of a neural network, we'll need a mathematical model of this simple switching action. Imagine the input value or temperature
Didn't mean to pause it there.
Is a point on a line. The position of this point depends on the input value. We can think of this as our perception space. It's one-dimensional because we only have one input. A neuron can be viewed as dividing the perception space into active or inactive regions. If the value is above the neuron's activation threshold, it fires down the output. And so when we train a neuron, we are moving this dividing line around by changing the weight of the incoming connection, which determines how much current is needed to trigger the neuron. Okay, similar to a thermostat where the
Let's go back and look at this example. So we have this number line, and so imagine this is temperature. And imagine that you have the idea of hot and cold, and you're trying to predict, is it hot or is it cold? Now, if something gets very hot, everyone would say it's hot. If something is very cold, everyone would say it's cold, but there might be some middle ground temperature that people would disagree about. And so you can imagine, let's say you had one neuron. This neuron would be choosing an activation point upon which it would be saying that this is a hot temperature. So you put in this value, let's say 6, whatever units that is, let's abstract away Celsius, Fahrenheit, Kelvin, etc. You can imagine surveying a bunch of people and saying, is this hot? Is this cold? Is this hot? And moving around this threshold. And then it's just basically some point, I'm simplifying it, but it's basically some point at which you are dividing the space. Below this level is cold, above this level is hot. Okay, but let's continue, because he's going to go into more dimensions and build this concept up a little bit more.
Current is needed to trigger the neuron. similar to a thermostat where the input is the temperature and the activation point is where we'd like the air conditioning to turn on. So let's consider a neuron with two inputs. Perhaps the input is a temperature and pressure reading of the environment. Now our model will have two variables which can each define a position along a dimension. And so together they can be thought of as a two-dimensional perception space or plane, where every input to the neuron is a point in this 2D space. In this case, the neuron can be represented as a straight line which partitions the space into active and non-active regions. Any input on this side will trigger the neuron, and any input on this side will not. And this pattern continues if we add more inputs. We just move up a dimension. Each measurement or input can be represented as a point in three-dimensional perception space. And the neuron can be represented as a plane which partitions this space into active and non-active regions.
So one thing I think sometimes people get a little bit confused about is this idea of dimensions. So you can I guess what is the best way of explaining this? But like a dimension is almost just like some axis upon which something can have a value. And so like some aspect, you can think of it like abstractly as like an aspect of something. And so what I mean by that is a lot of people, they think of, three-dimensional space. So we live in 3D, or you might watch a 3D movie where you can kind of see the depth, you can see the height and the width, and there's this space that you can move in 3D space. That's our lives. We live in 3D. But that concept of dimensions, I mean, people talk about like how many dimensions are there. That's kind of it's related, but it's not the only way to use the term dimension. There could be something that has many different dimensions. Like when you say, oh well, there's a book that you were reading and there's more dimensions to the book. That means there's more ways you can go down it and parse it, and there's more attributes to this. So like for example, at the example he's about to show is when you're thinking about weather and storms, there are all of these, there's all these attributes to the weather, and these are all independent attributes. And so there could be different levels of pressure and different levels of temperature and different levels of humidity. And all of these things can change independently of each other. And you could potentially have so many more factors that go into determining like what weather patterns are going to occur. And the thing is to keep in mind is when you try to visualize this stuff and show it visually and explain it, it gets really hard to show once you go past 3 dimensions. So it's easy to graph a dimensional thing with X and Y, and then you can do X, Y, and Z, and that's 3 dimensions. And you can show this kind of an example. But when you go beyond that to 4 dimensions, now our brains, when we look at this visually, we get confused because we don't have a really good way of visualizing it because we live in a 3-dimensional space. So that's just something to keep in mind. But the important thing is that there is a ridiculous number of dimensions that AI actually works with. And so we'll get more into that later, but I just wanted to point that out just in case anyone wasn't understanding.
Perhaps we want the neuron to act as a storm detector, for example. And so no matter how many inputs it has, a neuron is like a partition or linear separation of a set of data points in perception space. In higher dimensions, we just call it a hyperplane. This is how perceptions, which are values measuring the environment, can turn into concepts, where a concept is a region in perception space. That's how the neuron knows how to feel a storm if a measurement is in the right region. But of course,
okay, so what he's saying, he said hyperplane, that's a kind of a big word. Like that just means, so as he was saying, when you have a line that divides this 2-dimensional space, you have X and Y, you can have a line that divides points on those lines. If it's a 3-dimensional space, though, a line is only a 1-dimensional thing. So you then have to divide that, you would have a plane, which would be a 2-dimensional space, like as you see here. a plane. This is called a plane. It's dividing a three-dimensional space. And so now that you go above 3 dimensions, it's difficult to, like at that point, everything's weird. You can't really visualize it in a good way. And so therefore it's called a hyperplane because there's more than 3 dimensions. And so it gets abstract, but you see he's continuing with this 3-dimensional visualization.
Reality is not always so simple because we can't always draw a straight line through our problems.
Okay, I'm just going to keep watching this. Let's keep watching.
For example, imagine a situation where we have 2 kinds of input measurements, temperature and humidity. And our input measurements arrange themselves in a perception space like this. The circles represent measurements of winter days and the X's represent summer days. Well, we can't draw a single line to separate these points, but if we have 2 lines, we can, separating the data into 4 distinct regions. Each region is defined by the state of the neurons being on or off. If neuron 1 is on and neuron 2 is off, we know it's in this blue region. And that is why we need to use multiple neurons, so we have the ability to carve up the perception space into many more regions. And this is what the learning process does. By changing the weights of the connections, we move these partitions around to carve out regions around conceptually similar input points. So let's pause and summarize.
Well, yeah, let me pause and summarize, and then we'll see how he summarizes it. So essentially, as you see, it's not so simple. It's not always that you just have this one like cluster over here of temperature and humidity, and then like over here, all the points for no storm is here, and then all the points for a storm is up on the top, right? It's not always that simple. So there's a lot of data points, and it's a complicated thing to map out. And so we were talking about how an individual neuron can just divide this space with a line or a plane. But what he's saying is that actually you're going to need, since the shape of these things is not straight, you're going to sometimes need more than one division to map out these different basically sections of this space. So this is a temperature humidity space, and you need a complex shape. Like there's an actual shape within this space that represents storms, and there's a shape within this space that represents non-storms. And so depending on which part of this 2D grid, and in this example, gets activated, that is how you're going to determine if it's a storm or if it's not a storm. So if you kind of look at this line that he's drawing here, this zigzaggy line, if it were to be above this line, this would be a storm. If it were going to be under this line, it would not be a storm. And that's kind of there's the interesting thing is that this is the shape of the concept of a storm inside this 2D space. Well, we're going to build on this idea. So let's hear how he summarized what we've gotten through so far.
Conceptually similar input points. So let's pause and summarize. A perception is a list of measurements that are inputted into a network. These vectors can represent a coordinate or point in perception space. The number of dimensions in this space is equal to the number of different input values. And neurons act as partitions in this space. And a group of neurons together define a specific region in this space. And these regions can carve out inputs which are part of the same concept. But so far we've been looking at simple toy problems, and when we move to the real world, things get a little bit more interesting. For example, the first big commercial application of neural networks was vision, specifically making a machine which can understand human handwriting, so that at the post office they can read human letter addresses automatically. This is a hard problem because everyone writes numbers slightly differently, so the machine must find the general pattern of each number. In this example, the input to our network is an image containing 784 individual pixels, And so we have 784 input dimensions, each which measure the brightness of one pixel. Using our spatial view, we can think of the image of each written digit we input to the network as a point in perception space. And if we take many real examples and plot them in the perception space, we get this. The points are not nicely clustered into regions, but scattered all over. And so to carve up this space into regions is going to be very difficult. The messy distribution of inputs is why shallow networks with only one middle layer struggle to divide categories up cleanly. The way out of this problem, though, is to follow the way of nature. Organic brains use layers.
Okay, let me just pause here, and I just want to walk through what he said so far. So, okay, so the thing we were talking about with weather, where you're just trying to see is there high pressure and high temperature, well then there's going to be a hurricane, otherwise there's not. I mean, that's a pretty simple, relatively simple problem that you can just by hand kind of draw it out and show. This region of the graph represents a storm. This region of the graph does not represent a storm. That's simple. But quickly you get to, and you could almost do that by hand, by the way. You could almost code that by hand. It might not be super. With 2 dimensions, it would be reliable. If you wanted to add in more dimensions, it would start to become more difficult. So yeah, you could do that. You could do that by hand. You don't even need machine learning. But it's a great illustrative example of what is going on when you do machine learning. So now, though, right now we're getting to something where you cannot decompose the problem and just think about it yourself. This is something that's very difficult. Talk about this, and Andrej Karpathy is going to talk about this when he talks about software 2.0. So we're going to get more to that. But this is very difficult because look at these numbers. Like he's going to show examples. I mean, look at how this person wrote 6. I mean, there's all these circles. This is outline. This is lots of lines. This is square. And so you end up having this is there's like a bunch of pixels of this number 6, and it doesn't have to be like that though, because if you look at this 6 here, I wonder if I can zoom in. I can't really zoom in, but I mean, just look at this for yourself. It's this 6 where my cursor is different than this 6, which is different than this 6. Everything's different, and so there is absolutely a pattern here because we can recognize it. I mean, we're looking at this and I can read this easily. 4, 4, 0, 3, 6, 6, 1. So this is there's obviously a pattern there. But you can't simply say, okay, if there's this pixel in this location, then it must be a 3 or something like that. You can't write this type of simple logic. You have to find a way of taking this very messy array of possibilities and mapping it to something that extracts the signal, extracts the pattern, and I mean, basically carves out the space of all the possibilities. So here, this really is a great, and I don't know exactly how they plotted this, and I can maybe share some resources that do walk into how exactly they plotted this. I haven't gone deep into this literature, but I mean, think about the differences here in this array of numbers. I mean, anywhere could have a mark on it. Any individual spot could have a mark on it. Sometimes the 2 has this little squiggly loop. Sometimes it doesn't. There's so many different, things that go into these numbers. And so it is messy. Any sort of logic that if you were to write code manually that would decipher what is being written in these images just based on it being a literal array of pixels, a 2x2 grid of pixels, anything that you do, would be, I mean, it would be so complicated. It's very messy. There's not a clean way to just divide these things into the correct category. So this is essentially, in some way, they've found to visualize this. This is an accurate representation of just how disorganized this data is, and it really shows that you could not write an image like a handwriting class without doing deep learning. It's just not feasible, because look at this data set. This is some kind of like abstract representation of the diversity in this array of pixels. So let's continue seeing how exactly they solve this. How do they sort through this ridiculous cluster of number instantiations?
Any real examples and plot them in the perception space, we get this. The points are not nicely clustered into regions, but scattered all over. And so to carve up this space into regions is going to be very difficult. The messy distribution of inputs in perception space is why shallow networks with only one middle layer.
One thing I'm just kind of thinking off the dome here, but like maybe one way of looking at this is that you could think of. I mean, I'm not sure how they mapped this in 3D space, but you could think of, each of these as like this array here is, in a sense, it's a number, because there's some number of bytes that define the set of pixels, and so like you could perhaps it could be, I mean, it depends on how it's encoded, but you could even think of this as just a very long number with like 0, 0, 0, 0, 0, 0. Like every time it's black it's 0, and then I mean, I'm just kind of making this up, but like when it's gray it could be 5, or I don't know, I'm being stupid here, 5, I don't know why I said that, but there's some number once it gets to this gray, so 0, 0, 0, 0, like you keep going down, you're encoding this 0, 0, 0, 0, and then whatever, 2, 1, 2, because 1 would be white, 2 would be gray. I'm just making this up. 0, 0. Like you can think of this as represented as a number in some sense. And so maybe this, you can kind of think of this as if you took all the numbers that corresponded, like you took that number and you plotted it on some sort of graph. You would go in a certain location depending on what the number is. And now, like imagine I plotted it. Okay, I took this 3, I plotted it, and then I said, okay, this is where this number got to. This is where this number falls on this graphical representation, on this graph. And then you say, okay, now what number was it? Oh, it was a 3. So now we put 3 here on this label. And so if you do that a bunch of times, essentially, you're going to have this graph with a bunch of points all over the place, because all these, each image has its own unique number that it's plotted based on the data inside of the image file that goes and gets plotted at its own unique space. And then, but look, they're not lining up. Like there may be a little bit more 7s over here maybe than over here, I don't know, but it's basically, I mean, this is all mixed together. So even though the numbers that are the encoding of the actual data that went into that corresponds to these different numbers, even though they're all plotted, they're all mixed up in terms of what the actual values are. So there's no easy way to just say, oh, this is a low number, therefore it's 1. Oh, it's a high number, therefore it's 9. You can't do anything simple like that. It's just a very messy representation when you actually take the data and you say, and you try to just display it. It's all mixed together. So what we need to do is we need to carve out we need to create this crazy shape that's going to carve out all of the 3s. We want to divide, like you see here's a 3 here, another 3 here. Essentially, and this might be a slight misrepresentation of the reality, but we almost want to draw a bounding box that captures these 3s, dodges this 6, but then captures this 3, captures this 3, goes this way, and goes behind the 2, captures these 3s. And we want to have some kind of shape here that gets all the 3s into one region in this space. And we want to do that for every single. We want to do this for every single number. And I do think that's maybe not the best way of thinking about it, because what's going to happen is we're going to basically transform the location of these numbers into clusters and stuff. But the point is that that's one way of thinking about it, based off of how he has presented it so far. So let's just keep watching and learn more.
And plot them in the perception space, we get this. The points are not nicely clustered into regions, but scattered all over. And so to carve up this space into regions is going to be very difficult. The messy distribution of inputs in perception space is why shallow networks with only one middle layer struggle to divide categories up cleanly. The way out of this problem, though, is to follow the way of nature. Organic brains use layers of neuron activations to process their inputs. The importance of depth, or many layers, is the least understood aspect of neural networks. So let's pause and consider a simple analogy to understand why multi-layered networks are better at partitioning the perception space than a single-layer network. Imagine this is our perception space and we have two kinds of input data types. Each neuron we add in the first layer acts like a fold in this space. With two neurons, we can make two folds like this. And we could keep going, folding and unfolding the paper to carve out regions to separate these points. This will take 6 separate folds. This allows us to then group regions containing the same type of points using a final neuron which activates if any regions are active. But now consider what happens.
Okay, so imagine that this is the dog and cat images that are mapped out. And the red is dog and the blue is cat. So in this case, if any point within these regions, the blue, is activated, then it's a cat. The final classification would be a cat. And so, again, I mean, we kind of covered this, but the idea is, right, there's these regions that are divided by these neurons. The neurons act as a divider, and they map out these regions that correspond to the concept. And so what he's trying to get at here is that he wants to build on this idea of not just drawing these lines, but actually using folding of the paper as the way through which you are drawing a line, the way in which you're drawing a line through the space. And so you can kind of see how when you had this vertical line go this way, this horizontal line go this way, and this vertical line go this way, now all of a sudden you have these two spaces here. And so you could then add more smaller partitions by, let's say there was a blue one here, you could fold it there, and you could partition it more. But he's going to talk about why it's very powerful to have a deep neural network. So let's keep watching.
If any of those regions are active. But now consider what happens if we layer our folds. That is, we don't unfold after each fold. So let's do the first fold again, then the second, then the third fold across that layer like this. That ends up carving the space in the exact same way, using 3 folds instead of 6. And if we were to continue this process with a 4th fold, it results in 16 regions. And 5 folds results in 32 regions. This recursive power of folding shows how we can get exponentially more partitions using the same number of neurons if we layer them. Practically, this means that neurons deep in a network are not simple linear partitions, but are instead activated by a complex pattern of linear partitions.
Okay, so, he's going to walk through an example, but let me just lay this out. So let's watch him fold it this time. Let's pay attention to how he folds it.
Single layer network. Imagine this is our perception space and we have two kinds of input data types. Each neuron we add in the first layer acts like a fold in this space. With two neurons, we can make two folds.
Did you see that?
Like
so
this.
What he did was it was a completely unfolded paper. Then he folded it. Okay, fair enough. Wait, here we go. Unfolded. I'm skipping too far.
Data types. Each neuron we add in the first layer acts like a fold in this space.
And then
with
He
two neurons.
He did it quickly, but he unfolded it.
We have two kinds of input data types. Each neuron we add in the first layer acts like a fold in this space.
He unfolded it, okay? Now it's back again. And instead,
with two neurons, we can make two folds like this.
He folded it twice. Okay, now he did two folds, and he made 4 partitions.
And we could keep going, folding and unfolding.
So, see, he just did another fold there. He unfolded it, and he folded it, and he made another crease. So now he's adding partitions by unfolding it from a fully open piece of paper. Now look back here. You have all this line of neurons. Like, let's say here. What's the difference between having 1, 2? Like, let's say, let's imagine this is a very small neural network, and there's just these 2 neurons here, versus 1, 2, where there's another layer in the deep neural network. So this is deep, it goes far this way. So the difference, so what he's showing when he's folding the paper, just he unfolding it and then folding it in another way, it's still powerful to add more neurons. You can do more partitions. But that's like, I don't know what you call that, a tall neural network? I don't know what you call it, a fat neural network. I'm sure there's words for stuff. I just don't know much. When you unfold the paper and then just do another fold, that's like this. And it's good. It's good to do that. But then what he's saying is when you go deep, you can get a huge like exponential payoff by actually not unfolding it and just folding it again once it's folded. So let's watch him do this for real.
Type of points using a final neuron which activates if any of those regions are active. But now consider what happens if we layer our folds. That is, we don't unfold after each fold. So let's do the first fold again, then the second, then the third fold across that layer like this. That ends up carving the space in the exact same way, using 3 folds instead of 6. And if we were to continue this process with a 4th fold, it results in 16 regions. And 5 folds results in 32 regions. This recursive power of folding shows how we can get exponentially more partitions using the same number of neurons if we layer them. Practically, this means that neurons deep in a network are not simple linear partitions, but are instead activated by a complex pattern of linear partitions. And so let's look at how this works using a real-world example. Researchers took a neural network which was trained on real images, such as ImageNet, and then probed individual neurons to find out what activated them or what turned them on. If we probe neurons in the first layer of the network, we find they are detecting these patterns, which are looking for edges and points. Then they move to the next layer deeper into the network and probed those neurons to see what activates them. What they found was the next layers are activated by different kinds of textures. And deeper into the network, these textures get more specific. And as you move deeper into the network, the textures get more complex. And the deepest layers contain individual neurons that are activated by entire objects, such as dogs, wheels, houses, or trees. These complex activation patterns are possible due to the layered structure of the network. And so if we cut open a neural network, we'll find the deep layers contain representations of a perception based on what level of different things or patterns they contain, which is defined by how active those specific neurons are. For example.
So, okay, this is so cool. This is so cool. And you can go on this website, distill.pub. If you see down here, that's the citation. I can try and dig up the actual article, but there's not that many articles. It's a really cool blog that was created and then discontinued. But what they focus on is having really nice explanations for research, and they have all these great visualizations, and it's a really, really awesome resource. And so they actually published that. This is what he's taking is from something that they published. So go ahead and check that out. But The cool thing, so the thing I think is just so cool about this is, let's go, where was the, where was this really, where did he put all the different layers? Yeah. So in a sense, when you actually look at how this works, and this is, this is different than the training process. Like, this video doesn't get into backpropagation and gradient descent and that kind of stuff. And it is worth talking about. I'm definitely going to talk about gradient descent, because that's something that Andrej Karpathy talks about. But maybe I should also just for a second talk about backpropagation at this point. And so basically, backpropagation is almost, when I heard the term backpropagation, I had an idea of what it meant. And when I actually learned what it meant, it was what I thought. Like, basically, I mean, the way that a neural network works is that you feed information into it. So you put in an image, and then like, let's forget about how things work, why it works, anything like that. Okay, let's just forget about these. What are these neurons? Like, what is that doing? What's going on? Who cares? It goes boop, 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 boop through the network, and then it gets a result. Now, like, imagine you just did this the first time. It's not going to know anything. You just started training it. So you put in an image of a dog, and it says, oh, it's a cat. Oops, that was wrong. So what do? You like, okay, well, how do I say this? You figure out how wrong it was, and the direction in which it was, how wrong it was, and the direction of wrongness it had, and you go and you correct it. So let me give like an example of better than dog and cat, because that's maybe a little bit like that ends up with all these concepts that we're talking about here in this image. So let's talk about hot and cold. Like, so let's say that you say it's 1,000,000 degrees, and it says, oh, that's cold. You would say no to the neural network. You say, no, that's hot. It's very hot. So you're very wrong. So you need to just completely lower your expectation for cold. So whatever you did, do the opposite of what you just did, and severely do, like you weren't even close. And you basically tell that to each neuron. So you go forward, you have each neuron active. Like, we've talked about this, like you've seen this visualization of the neural network. I'm going to find, like, right, it goes forward, 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 right? It goes starting here. Here's the data. Here's the answer. And then depending on how wrong it is, you tell each of these neurons, this was wrong. You tell these guys, this was wrong, this was wrong. So everyone updates their activation function according to the input of or according to like how well it performed, essentially. And if you just keep feeding this in, seeing what was wrong, and then telling it how much it was wrong, and going backwards and adjusting each of these neurons, then the neuron will store the information that will allow it to consistently contribute the right information to the whole network. And so that's how training works. It's literally like almost like training students or something. Like, they get the wrong answer, you say, no, that's not wrong, that's not right, here's where you were wrong. And then next time, that's something that they can potentially do better, hopefully. So that's what backpropagation is. And so now let's go back to this. So now what we're seeing is that now we're not treating this as a black box. Instead, we're actually seeing this, we're seeing what the individual neurons, or at least the layers of neurons, are doing, which is super cool. And we're seeing that the ones in the beginning, they're just getting just certain, like, very abstract, like they're just extracting different components that don't really give you an answer to what the thing is, but it could be something that's relevant. Like, for example, let's say that you're looking at a house. Okay, a house is going to have very straight edges. It's like a wall, a straight wall. But then let's say you're looking at a strawberry. A strawberry is going to be very curvy. So these are very different, right? Or there might be like more red in a strawberry, right? And blue in a blueberry. So that's a kind of thing where it's very it's very, these factors are all relevant in assessing what is a strawberry, what is a blueberry, what is a house, etc. But if you just know it's blue, you don't know it's a blueberry. It's not, that doesn't just tell you the whole all the information, but it's very important. And so, and as you can see here, this shows that as you go deeper into the network, these neurons become increasingly responsible for higher levels of abstraction, of understanding about of what it is. So you might have something with like straight edges, like what are the things with straight edges? You're kind of partitioning the space in some sense. You're narrowing in on things with straight edges, and now you're saying now bumpy things with straight edges, and now you can just keep going down, and you can. I don't even know what's bumpy and has straight edges. That was a really bad example. Let's say smooth and straight edges, and then space gray, and then, oh, this is a MacBook, right? So, I mean, whatever, a stupid example, but you get what I'm saying. It actually is increasingly narrowing in this super ridiculous multidimensional space of concepts of all the things that AI can do. It's narrowing in on the thing that you're looking for. And yeah, so let's just continue watching.
That are activated by entire objects, such as dogs, wheels, houses, or trees. These complex activation patterns are possible due to the layered structure of the network. And so if we cut open a neural network, we'll find the deep layers contain representations of a perception based on what level of different things or patterns they contain, which is defined by how active those specific neurons are. For example, an image of a dog would light up the dog-like patterns in the network. Finally, let's flip back to the spatial perspective to see this power of layers in action. Recall that our input, such as an image, can be represented by a point in perception space. And each of the following layer activations can be thought as moving that point to a new location. And it finally settles into a final space at the end of the network we could call concept space. And critically, the job of these transformations is to pull apart dissimilar points in concept space and push together similar ones. To see this in action, let's return to our real example.
So if you didn't catch what I had said earlier about carving out the space and making this weird shape, I mean, it's definitely it's a valid way of thinking about it, but it's actually what you're doing is you're creating a function that transforms like the input space, perception space to the output space. I'm not sure what the exact words they use on this, but I'm going to get into this a little bit more after the video. So let's just continue watching. I'm just going to back up so that you maybe concept space. That's what they call it, concept space. Perception space to concept space. Let's just watch this whole thing one more time. Okay, starting here, let's go.
Finally, let's flip back to the spatial perspective to see this power of layers in action. Recall that our input, such as an image, can be represented by a point in perception space. And each of the following layer activations can be thought as moving that point to a new location. And it finally settles into a final space at the end of the network we could call concept space.
Okay.
Critically, the job of these transformations is to pull apart dissimilar points in concept space and push together similar ones. To see this in action, let's return to our real example where we plot the points of various perceptions of different human-written digits. Notice at first the points are all over. But as these perceptions move through the network, gradually these points are separated into tighter and tighter clusters. And so each layer acts as a transformation that gradually disentangles these points. This allows the final layer of neurons to easily partition the data into separable regions, which represents the concepts, in this case numbers, we are looking to classify. And
so let's go back here for a sec. This is so cool. So remember, everything was mixed up. And you could think of each neuron as a transformation. And so, or at least maybe it's each neuron or each layer. I'm not fully clear on how you should think about that, but I guess you're saying each layer in the deep neural network as it is a transformation. And so what it's doing is it's basically sorting these things into very clear buckets. And this is the concept space. So now the concept of 4 is in this region. I think that's a 4. I think I'm reading that right. The number 4, though, is in this area of concept space. And so it's very easy to say, like where, but basically you can do something where you can say, okay, I have this point. Is where, like, what is it closest to? Or what region does it fall in? Oh, it's right here. It's in the 4 section. It's closest to the 4 area. And you can kind of look at the distance of something and classify it in that way. I think it's something along those lines. So maybe you would have like less confidence. I could be wrong about this. I'm kind of speculating here. Like maybe if there's a point here, if you see my cursor, it's pretty close to the 4s. So you would say with low confidence, it's a 4. And then maybe if it is right here in the middle, you would say, oh, this is definitely a 4. And that's how AI can make predictions. So how deep neural networks can make predictions. They're taking this mess and they're applying a set of transformations on it, and it goes from this perception space, which is the way that it is encoded as data as the input, and it's basically like the neural network itself is a function, and this function transforms the point. Well, it transforms the point in the perception space to a point in the concept space. And then based off of that location in the concept space, you can classify that original input. Okay, let's keep watching.
Concepts, in this case numbers, we are looking to classify. And so the magic or true power of a neural network is entirely in this layered processing, because it allows the final layer of neurons to carve up concept space where the points are nicely clustered, instead of perception space, which is hard or impossible to protect.
Okay, so like also just to amend what I had said, I guess this corresponds not to the final classification. So there's one other set of, I suppose you would call these neurons at the end, but these clusters are, they basically, this final layer cleanly divides it. And then you then remember how those early examples where you just drew the line and divided hot and cold. Well, you can basically just use this final layer of the neural network to just segment the data and say it's in this region very clearly. Therefore, simplistically, you can easily say this is the number 4. But let's continue watching.
That's how a neural network knows something is a number 3 or 6, based on the proximity to the 3 or 6 cluster. This partly describes why we have different mental feelings or intuitions when we see different objects. It's because different groups of neurons are being activated deep in our mind, depending on what cluster it belongs to. And these clusters can also be thought of as connected regions or manifolds. And so perceptions representing the written digit 6 would fall on one manifold, and the digit 3 would fall on another. And so manifolds are spatial regions which represent the patterns essential to a concept. These patterns are defined by the connection patterns or strength across the neuron layers. But so far we have only modeled how intuition works, that is, a rapid interpretation of some impulse, such as when you recognize someone's voice by a single syllable. This is what a single pass through a neural network simulates. The other big challenge is problems which require reasoning. Interactive problems, such as having a conversation or playing a game. These problems are sequential in nature and require things like a form of working memory. This leads us to the cutting edge of neural network research. How will a neural network learn to reason?
that was that. And this is a pretty old video. This is 4 years old. Um, it's not clear to me when this was relative to ChatGPT, but my intuition is that this was before. Yeah, it's probably, I mean, obviously, like Transformers existed, the Transformer architecture that powers ChatGPT existed at this point, but I'm pretty sure Chat not out. So AI had yet to be as big as it is now. I mean, it was really ChatGPT in combination with um, uh, Dolly and Stable Diffusion that really started blowing people's minds. And maybe you could say GPT-2 was also pretty big, but maybe this was around the same time as GPT-2. But I think a lot of people did not, at the time, recognize the significance of GPT-2 until it was packaged as ChatGPT. And that's actually a really interesting topic. It's related to crypto. I do want to get into that at some point about because when we're thinking about like crypto apps and the effect of UI on how crypto is used, there's lessons to be learned from how UI has accelerated AI. So let's talk about that another time. But I want to kind of just tie some of these concepts together just a little bit more, and then I want to go jump into Andrej Karpathy's video and finish that. So, okay, I'm on TL Draw. Let me expand this window a little bit. Okay, so the first thing I just wanted to point out is that a neural network is kind of like a function. And so if you remember math class, you have an X and Y axis, and you would have, if you remember, like this is like early math, you could have some line formula, like Y equals, oh gosh, this is going to be hard to write, with MX plus, oh no, I'm really slow at writing this. Okay, I'm going to probably try and type things from now on. But okay, so let's say that you have like this is the line, right? This you would you can represent you can represent the line with this formula, and then what you remember. So you remember X and Y. Everyone knows that. And then at some point you learn, for some reason they never really explain this to you, but there's this thing called f of x, and then they just say, oh yeah, yeah, you just write f of x instead of y. Like, don't worry about it. Well, that's because y is a function. And you can x could be a function too, but in this case, y is a function and x is the input. And so I'm just going to say a question mark because I don't want to write this. Okay, so let's pick some values for this. We'll say y equals 2x plus 1. Okay, this is our function. Okay, y equals 2x plus 1. So you can see the way I plotted this is it intersects at 1 here, and 1, and then wait. Yeah, so then at 1 here, it would be at, sorry, this is so bad, 2. Watch me like get this stupid thing wrong on live, but whatever. Okay, simple stuff. This is so basic. Okay, but now we have a function. So what is the function doing? The function is transforming. So now let's say you have, what is f of 3? Okay, so well, first of all, let's establish it. This means f of x equals 2x plus 1. So basically, when you put when you put, let's say, 3 in here, you're getting 2 times 3 plus 1. That equals 7. 7 is behind this. How do I close this? Oh God. Okay. So we have 7. So now that means that when we have 3 here, it's gonna go here. This is obviously not a real, wow, I already did this wrong. This was supposed to be 3 because it was 2x plus 1. And this is 7. Okay, this is not drawn to scale, guys. So this is how this is a function. Everyone's learned about this in math class. This is really basic. So yeah, so what is a function? Like, let's just talk more about this. What is a function? A function is something where you provide an input and you get an output. And so there is, in a sense, you can think of a function. Sorry, I'm not good at using this TL draw platform. I'm just going to erase this. Erase this. Okay. I wonder if I can make this bigger. Okay. So in a sense, this function f of x, it takes x as an input, and you can think of it as a transformation, because what it does is it takes the value of whatever is in x and it stretches it out, meaning it, or whatever. I mean, you can think of it in many different ways, but it multiplies it by 2, it doubles it. It takes x, which was 3, it doubles it, now it's 6, and then it pushes it up by 1. So like, let's just, again, do a really, really bad drawing of this. This is so bad. I don't even know. This is embarrassing how bad I am at drawing, but I should have thought this through a little bit more. But okay, here's just x plotted by y, right? And then when I'm stretching it out by 2, now, can I change colors here? Okay, now I'm making it go, wait, no, this is steeper, it's steeper. So now every time it goes up by 1, every time we increase x by 1, now y is increasing by 2. And then what happens, then we're also shifting it by 1. So now we have to actually shift it up. That's what's happening here. So this is a transformation. It transforms, is one way of thinking about it. I'm not saying this is the only way of thinking about it, but let me, whatever, do this. In a sense, this line is transformed into this. You can think of it that way. And I mean, that's really not a good way of thinking about it, but I mean, maybe it is. I don't know. But the point is that maybe not the line itself, but the points on the line. I mean, the point is you have a value of x instead of being represented where x equals y, right? You're taking x and you are transforming it into y. And that's what a function is. It has an input and an output. And there's something that happens in between that, that facilitates this type of a transformation. And so now, if you study computer science, and it's been a while since I've gone through this material, but another thing that you realize is that that functions, software is just functions. Functions are Turing complete. And so you can go and derive everything in lambda calculus and see how you can use functions to do everything. But essentially, I mean, and especially if you think about blockchain as an example, a function is going to be there's like a state transition function. So you have some data, some initial data. That's like the genesis of the chain. You have a function, and you apply that function with new incoming data on the old state. And so I can just try and draw this, right? You have like a function, and then you have the state, and then you have the data, and then that produces the new state. And so every time you have a block in the blockchain that comes in, let's say that was the old block, okay? And so here's the state is in this block. And then now this has a bunch of transactions in it. We'll call these transactions. This is really bad, but you get my point. Okay, so you have a bunch of transactions here, and this is D, and this is in the block. And then you have this thing called the state transition function, which is this F. And then when you take the old state and you apply the data from the new block, and then you get the new state. This is all software works like this. This is what software does. And so the reason why I'm even bringing this up is because essentially a neural network is a function. And it's just like normal software. I mean, you can think of like even what your web browser right now. There is memory on your computer, and there's data on your computer. It's taking that data, and it is continuously looping and doing this multiple times. So that's not to say that it's all purely a function in a sense, but based off of the data that is in your computer, it is rendering something on the screen right now. And it's continuously doing this, and that's what software does. And meaning it's translating the data into pixels. It's translating the data into audio that's coming through your audio device. And so as you're communicating, it's constantly communicating with the network. It's constantly looping and taking whatever data is in your computer and then determining what external packets to send out to the network and stuff like that. So that's what software does. And software is essentially just a bunch of functions, something that takes data and transforms new data, and it interfaces with the architecture of the computer to do certain things that you can interact with, and you can use it in the way that you do. Similarly, a neural network is also a function. And a neural network is taking this input data and it's transforming that, taking it from this perception space to this concept space. And it's a super high dimensional transformation. I mean, I don't even know how many parameters, as they say, are in these models. Llama has 405 billion parameters. Now, I'm not sure what that means in terms of how many dimensions that data is, but it's super high dimensional, and it's taking very messy amounts of input, and it's basically transforming it into something where it can predict what the next word should be, and it does a really good job. And so with this understanding of like the equivalence of software in general to neural networks and how these are both the same thing, this is going to provide us with the context needed for understand. Basically, think of it this way. Like this is going to tie into the next video that we're going to watch with Andrej Karpathy, talking about software 2.0. Essentially, what I'm trying to say here is that this is a search problem. We're searching for the function that does the transformations in the way that we want. And if we are able to understand the problem very well, we can write by hand. And you can write like a purely functional application using lambda calculus, and you can use Haskell, and you can make something that's basically a pure function. And if you can break down the problem, you can make that function yourself if you understand what to do. But if you don't understand what to do, now this is where software 2 comes in. So I'm going to speed run through the first half of this talk, and then we'll go and do the rest of it that we didn't get to last time. So let me just, I'm just going to kind of look at his slides, and I'm going to talk about it with you guys. Okay. Okay, so first, he talks about this idea of engineering. The traditional software engineering is called the approach by decomposition. So, in order to make traditional softwares, you're basically making, like, remember we were on the whiteboard, and I really badly did this y equals mx plus b. It's a simple function where f of x equals mx plus b, and so it kind of stretches it out. The m factor stretches it out, and then the b factor adjusts where the point lies. That's a simple function. I understand that. That's very easy. And so I wrote that myself, and it was pretty easy, pretty awesome. But now you can imagine you want to make something that is more complicated. So now, if you can understand all the steps involved, such as, okay, first we expand this value, then we add to the value. Like, if you understand all those things that you want to do, you can get that, you decompose it, break it into tasks, and have engineers build each step of that. That's how normal software is built. You have product managers that make a plan product, and then they create tasks, and the engineering managers say how long it's going to take, and they work with their team to break it apart. They might say, this is not possible, we can't do this, but they're going to come together and come up with a product they designed, and it's going to be, every line is going to be written from the ground up to do the thing that needs to be done. And there's lots of tools, like we're as software engineers, we're standing on the shoulders of giants. So using all these existing libraries, and we're using these powerful programming languages. We're not writing each instruction for the computer by hand. We're able to automate a lot of this stuff and work at a very high level of abstraction. But nevertheless, we are still manually encoding the logic for how the function, I'm going to call software functions from now on, because that's how we want to think about it here. We're breaking apart the function and exactly specifying what it does under all circumstances. And sometimes we can get away with ignoring certain things, hoping that the function never has to deal with that. And that's a practical trade-off that we can make. But for the most part, we have to fully understand everything and write it down. That's how software development works today. And so, as he is pointing out, is that this is, it works well, it's very cool, but it doesn't work for certain types of tasks. So it's very hard to break apart an image recognition problem into a function that a human can write. A human doesn't know how to, because there's all these things, like you want to detect the ears of the cat and the eyes and the shape of it. And how do you differentiate that from a dog? How do you, what color is it supposed to be? I mean, there's just so many things to think about that you couldn't even begin to write something that translates. And remember, we're not talking to a person and telling them how to recognize a cat, because we have these recognition systems in our brain already. I'm talking about, you could imagine someone who's never seen a cat, you could try to describe it to them, and maybe you would do such a good job that they would be able to recognize a cat when they saw it. It's possible, but that would be based off of the neural architecture that we already have as humans, and the fact that we are primed to recognize animals and understand features and ideas like that. That's not what a computer does. A computer is dumb. A computer just has a list of pixels, and all these are pixels, and that's it. It's just data. Just like we saw that list on the neural network earlier of the data coming in. That's all it is. It's just 5, 7, 6, 3, 2, 9, 8. It's just numbers. So for those who don't write software, it's actually not a very difficult thing to do. You're just saying, if the user typed in A, or if they click it's really high level stuff. You're if they click the login button, then redirect to the login screen. That's really how hard it is. It's not, you're not parsing bytes and stuff like this. And you're definitely not doing that on a, I mean, sometimes you are, but not on a very high scale where you're somehow like basically the point is just take my word for it. If you don't have any intuition on this, that's a very difficult thing to do by hand. So, okay, so essentially, the way that it used to be is that they would spend a lot of effort in when they were doing image recognition into breaking down the image into the way that they could. So like as he's saying, like they would take out the edges, they would I mean I don't even necessarily know all the stuff that they would do. They would break it apart, and then they would find the patterns that come together to commonly make the outcome, or to help them determine what the classification would be. So like they would use some neural network, but the input to the neural network would be a bunch of what's called features. So they would have all these techniques to extract different elements, like this is like a stupid example, but let's say you're trying to classify fruit, and if it's blue, you could extract that feature of color as blue, or you could extract a blueness feature, and then you could input that into the model. And so you basically break down the problem, get as many different features as you can by thinking about it, and now maybe the AI will now know it's blue, so it's a blueberry. But the issue though is that doesn't work very well. But that's what they used to do. They used to try to break it down as much as they can by hand, do as much of the detection as they can, and encode as much of the logic as they could into the detection process, and then have the AI just do the minimal thing of kind of combining roundness, blueness, berryness is not something, but maybe smallness or whatever. I mean, I don't know. It's very difficult the way that it was done, and that's why image recognition didn't really work very well in the past. I think what he's kind of saying in these slides is that this works okay and maybe in the lab for some primitive examples, but look at the diversity of all of these images of cats. I mean, these are so different. There's almost nothing similar about this black cat and this white cat. I mean, there is, but look, these are dark eyes, these are light eyes, this is dark, this is light, this is just so different. Like, this is like, yeah, what is this? There's no eyes here. This is the light shining through, but yet we know this is a cat. This is very clearly a cat. So how can you do this? I mean, how can you extract these features manually? So yeah, I mean, basically, maybe even here we weren't even using neural networks back in the 80s and 90s. I think we were though. I'm not an expert on the history of visual recognition, but the point is he's saying we basically, scaled up this approach. There's things called like convolutional neural networks, and I think that what those do is they are able to kind of like extract like interesting. I'm probably going to butcher the explanation, but you can watch some cool YouTube videos. But they're able to like detect like interesting like visual patterns in different images, and that could be useful for feeding into a neural network. But anyway, so I'm just going through this really quick. The thing is, though, is basically the point of what he's trying to say about the history. And he goes through it really fast. So if you think, oh, I did a bad job of explaining it, he also just breezed through this history of machine learning in the talk. So it's not like you're not missing that much, but it's good. I mean, it's maybe worth going back, and you should definitely watch this whole talk on your own without my reaction. It's a very important talk. And it could be interesting to learn more about the history. But the point that he's making is, okay, yeah, in the 70s, there was no learning. There was no neural networks. It was just literally hard-coded things. Like they would detect edges and they would say, okay, if there's this type of edge, then this is what it is. I mean, this is such a limited thing. You can basically not do anything. And then over time, we would extract these features, and these features okay, yeah, now I'm understanding things a little better. The features would go in and feed into the classifier. And so you can use a neural network or maybe some other type of classifier, saying a linear classifier. I'm not sure what exactly that means, but there is some kind of classifier. And then you would just feed in these features, and if the right combination of features suggests that this image is classified in a certain way, then it could work. Then they have convolutional neural networks, where I guess the idea of that is it can kind of learn its own features, but you still have to deploy in a very tactical way. You have to use the convolutional technology. I'm not saying this the right way, but you have to use these convolutions in a way that is tailored to the use case, and it's difficult to do. There's still a lot of manual setup that you need to do, and you have to think about the problem, you have to decompose the problem, and it takes a lot of manual work. So at least you're not like identifying all the features yourself and feeding it into a classifier. At least you're able to automate some of that, but you're still doing a lot of work yourself. And now what he's saying is basically we're going to a completely automated future where you don't have to really set it up at all. You can just provide the data, and you can and it will just be able to handle all of this itself. And what we're seeing is not only are we able to now, by just giving more compute and more data to these applications, or like in this process, by using more compute and more data, we're actually able to do less engineering. We don't have to decompose the problem anymore. We actually get better performing models that are, in a sense, easier to make if we run with this idea of training the end to end. And this wouldn't have been possible if we had slow computers. So a lot of this breakthroughs in AI does come from the fact that we've made, with Moore's law, we've had computers get faster and faster and faster exponentially over time. And we've also had huge data sets generated on the internet. And but as you can see here, like AI is getting better, and the way to do this, the way to make it better, is by scaling up data and compute. But here's the issue. The issue is when you're dealing with lots of data and lots of compute, that itself is hard. I mean, you need to construct a high quality data set that's massive, like a big data set. You have to manage that. You have to deploy it and train it and have massive data centers run the compute. And this is, in a sense, what Software 2 does. Software 2 is the challenge of setting up this hands-off approach where you're not able to do it all yourself. You're not able to break down the problem yourself and manually engineer it. Instead, you're sitting back. You're saying, this is too complicated to actually make myself. I'm not going to be able to do a good job. So instead of doing it myself, I'm going to throw compute and data at it, and we're going to have the compute and the data solve the problem in a way that I, as an engineer or as a team of engineers, never could. So this next part I think is very important. So what he's talking about here is this is the program space. And you can kind of think about this, and we were just talking about the idea of a perception space and a concept space. And so you can kind of understand, like a perception space would be all the possible inputs that you could feed into a neural network. And the concept space would be all the concepts that the neural network has classified into clusters. And the program space, you can think of this as all possible programs that you could feasibly create or run on your computer. So this is basically this, so let's say I code some software and I send you the GitHub link. That would represent, in this program space, that would represent 1 point in this program space. And so some other software would be another point. Each potential program would be a point in this program space. And so there's some very simple programs and there's some very complex programs. So an example of a simple program would be Hello World. That'd be super simple. It would be right here in the middle. Now you can imagine like ChatGPT is an example of very complex software, because basically you type anything into it and it will come up with a high quality, understandable response for anything that you could imagine asking it. That's crazy. Like, there's no way that a person themselves couldn't answer questions like that. So how could you create software? I mean, even a group of people couldn't answer questions like that. It's not even, people can't even conceive of the capabilities that ChatGPT has. How could you then create something that does that? You're not doing that by hand. You're not writing, if this happens, then you do that. You're not like laying out this logic manually. You're not creating this function manually. That's not what you're doing. Instead, there is a function. Like the function, I'll tell you what the function does. You send the prompt. Like it's like you look on the ChatGPT API or the OpenAI API, just go Google, look at that's the function, right? When you do a completion on there, that's the function. You send in the prompt, that's the input, and then the output is the response. That's the function. But you could not possibly imagine writing that yourself, that logic yourself. It's just too complicated. Same with self-driving. This is what he's talking from. He's talking from experience here. He has a lot of experience with. He was running self-driving at Tesla at this time, and so he's drawing from that there. I mean, that's so hard to make self-driving cars. Now they're very good because they've gone in this direction of software too, where they're doing less work themselves. So anyway, that's what he's saying here.
This is software.
Sorry, I didn't mean to play this. Okay, so now let's forward. Go ahead. So now what software 2 does is, you still want a point on this space because that's a function. That's a function implementation. But what software 2 does is searches for that dot, but it tries to find a dot that does a very good job. So, let me just continue forwarding. So let's say you start here and this isn't very good. It doesn't do a very good job. Like, let's say that this is just, you just randomly try to make ChatGPT yourself. It just completely fails. You try to hard code everything and ChatGPT is horrible. It's really bad. That might be this point here. That's like the starting place. But basically, then if you, instead of thinking about manually created software where you write and compile code, instead you think of a neural network as a function, which is also a piece of software. What you're doing is, by training, remember we talked about backpropagation, how it adjusts the weights of the neurons. You're training basically as you feed in data, and it takes a lot of compute to do this, but you just do this a bunch of times. I mean, if you just do this a few times, it won't work. You have to do it so many astronomically number of times, like an unbelievably, unfathomably high number of times. But if you do that and you are giving it the data so that you're adjusting it in the right way, now you're searching for a good implementation, and then you actually have the weights. You have these weights that can be loaded into a neural network and then can then transform this perception space into a concept in a really good way. So you put in the prompt, you put in the message to ChatGPT, and then it predicts the next token. It keeps doing that, and it keeps classifying whatever was before into what the next token should be, and then it's basically producing a really great string of words that can be sent as a response from your input. And it would be impossible to come up with this yourself. But by just having a ton of compute and a ton of data, you are able to do this. And this also applies for self-driving cars. So he's going to talk more about self-driving cars. Okay. But before that, he talks about gradient descent can write code better than you. I'm sorry. And so what this means is basically, okay, now I'm thinking I'm going to butcher this explanation of gradient descent again. Last time I gave an explanation of gradient descent and it was really bad. But like, I'm going to try doing it again, but please don't make fun of me. So first of all, I want to preface this by the fact you can go and look on YouTube for explanations of gradient descent. Like, so many people, it's such a common, basic concept. So you are more than welcome to do that. Please do that, as well as watch this. But I think 3 blue, 1 brown explains gradient descent, but other people do too. Okay, anyway, I'm going to kind of explain it in a different way. Okay, so let's say there's a mountain. One sec, let me undo that. I'm going to do black. So let's say there's like a mountain top and a valley, and let's say there's a hill over here. Okay, so you are a person. I'm drawing a person. And you have a cell phone. And over here is a cell phone tower. And you cannot get signal. Now, we could frame this in a million different ways. So I don't want to like interpret any given specifics on this example. But okay, so you want signal. So now imagine that you know that you could get signal at the highest point of this landscape, which would be here at the top of the mountain. Okay, so how would you do that? How would you go there? How would you go to the highest point to get signal for your cell phone? Now, it seems very obvious. You just climb the mountain. What do you mean, how would you get there? Yeah, that's true. You would go this way. You would climb the mountain. But the thing is, that's kind of built into your own brain, because we as humans have a natural perception of space and time. So we know you just climb up the mountain. You see a mountain, you recognize the mountain. This is built into our psyche. We understand this. But it's not necessarily an intuitive thing. Like, how do you explain to someone where you go? You just say go up the mountain. I mean, that could be just synonymous with to go to the highest point. Just go to the highest point. How do you do it? What's the process? Well, like, do you go straight? Do you go to the side? Like, how many steps do you take? Like, what do you do? Where do you walk? It's a trivial thing, but I think going through this trivial example will help build the intuition for what is actually going on, because it's something that you do understand. Well, the way that you do it is when you're seeing the point of a highest incline. Like, if you see a point that's going down, like if the ground in front of you is going down, you don't walk that direction. You look for the point where the ground is going up, and you go that way. Like, I know it sounds stupid to have to say that, but that is what you do. That's how you climb the mountain. And that is basically gradient ascent. You're going to a maximum point. And now, let's say you were here and you went this way and then you went up here. You could follow that algorithm to this maximum point here. But if you then continued saying, okay, I'm going to go to the highest point from here, you would, every direction that you go, nothing would be higher than this point. Even though this is higher over here, gradient ascent going to the maximum point on this landscape, so to speak, is not going to get you here, but it will get you to whatever is the closest maximum. And so that's basically what the gradient descent is. So gradient ascent, gradient descent. Gradient ascent would be finding the highest point, and gradient descent, which is what people usually talk about, is finding the lowest point on this landscape. And so imagine you're just here and you wanted to go to the lowest point. Like, let's say now you're here and you just want to go to the store. And the river goes to the store. This is so weird. I don't know why I'm doing this. You want to take the river, take the boat to the store. So you're going down. You know the river is at the lowest point. So you're following the river. Now, how would you do this? Well, you walk down. It's quite simple. You look what direction goes down the most, and you go that way. Like, you don't go this way, you don't go this way. You find what goes down and you go that way. Now, if there's so it's a little, let's talk about going up again, just because it might be a little more intuitive. You're going up the mountain. Now, let's say that the mountain was like this. You're walking here. It's not very steep. You're going to take a gentle step from here to here. Now, imagine that the mountain is very steep. You're going to put a lot of force going up. You're going to put a lot of effort into this. You're going to take a big step up the mountain. You're going to exert more energy up the mountain. And basically what gradient descent does is, let's just talk about gradient descent again, and let's just stick on this idea of gradient descent. You're going to the lowest point, so you're following the path. You're saying what is this direction of the slope, and let's follow that direction and go down to the lowest point. And depending on how steep it is, if you see that this is this is, again, maybe the analogy falls apart, but if you see this is a cliff that is going down really fast, you will basically you will go far. You'll take a very big step. I'm just going to go back to I'm going to go back to climbing the mountain again. Sorry for mixing this up, but it's just so much more intuitive. When you're climbing the mountain, here's the mountain. When you see, this is very steep here. This is not very steep. So this is the top. So when you're here, you want to get to the top. You don't want to overshoot the top. You don't want to be here. You want to be here. So it's not very steep. So what you do is you take a small step and you go here. This is very steep. So you take a big step because you know that it hasn't plateaued yet. So you know you still have a long way to go. So you're going to take a big step. So this is basically how gradient descent works. It goes towards the point that it's trying to reach by just looking at the shape of the data when you plot it out, essentially. And depending on how steep it is, how quickly it's going in that direction, you just keep taking step after step. And when you're training something with gradient descent, it's like you're taking a step in the direction that the descent tells you to go. And so when you have these neurons that are being trained in a neural network, they are being adjusted in some direction and with some magnitude. And so, like, let's say you're on this mountain, you're going down here, You take a very big step. Let's say you land over here. This is maybe unrealistic, but let's say you did. Then you would actually reverse direction and take a smaller step until you get to the real bottom here. That's how gradient descent works. And so what it is it's a method for searching for something. So what he's saying is that if we go back here, he's saying that basically this optimization process, this is called optimization because this is a maximum. This is a minimum point on these landscapes. So they are also called optimum. They're optimal. Like this is optimally high and this is optimally low. So it's optimization. You're optimizing something. And in a sense, you're searching for something. You're searching for the highest point. How do you do that? You follow the incline. How do you find the lowest point? You follow the decline. And that's what you're doing here. You're searching for the best implementation of this software, this function. And so I guess the point is that he's saying that this process can do it better than you can. That's what he's saying. That's the joke. I just wanted to explain this joke because last time I tried to explain it, I did a very bad job. And I guess the one of the things I'll say is like, what exactly are you searching for? Usually it is the error of the prediction. So if you make some sort of classification, like you can predict, for example, the next word, and there's an error. You can measure how wrong that output was in the training process. So it was supposed to say dog, but instead it said cat. That was very wrong. It should have been dog. That's wrong. So now that error, so you quantify the error, and then without going into the technical details, you minimize that error. So if you can map out the error like a landscape, imagine you could do that. It's just a shape. I mean, everything is just a shape. This is a two-dimensional shape. Everything has a shape, as we were kind of discussing, a multi-dimensional shape. You're finding that low point where you have the minimized error. And that is the way in which you're training the network. Okay, let's go back to Karpathy. So we made the joke, very funny joke. It's a great joke. I don't remember what he was necessarily saying here. But he's putting some caveats on this. So he's saying that this works. He's saying software 2 works. Gradient descent can write software better than you can, write code better than you can. And now he's even saying you don't necessarily need a data set. If you have some sort of criteria for measuring the error, you can optimize the error. So as long as you can measure it, you can measure the efficacy, you can run an optimization process that searches for the best implementation, but you have to have the compute. So it's not just data, it's compute. But you need an evaluation criteria, basically. And he's also saying, this is cool, I need to look more into this, but you don't need neural networks. You could do some other kind of optimization process. So this is cool. I need to go look into this some more. This seems really cool. Like, how would you do this without a neural network? So that's awesome. And so now he's talking about Tesla. So he does this at Tesla. So basically, initially, they had a lot of code that they wrote by hand. Like, so for example, they could identify where the lanes are, and then they could say, okay, if this lane is here and this lane is here, you want to be in between. So we're gonna measure the distance between each lane that the car is, and you can steer make sure you're steering in the middle of the lane and stuff like that, or maintain this distance between the car. Like as long as you can detect how far the car is, we can like code in, like, don't get closer than this amount, accelerate if you can up to the speed limit. You can imagine all the handwritten logic that can go into self-driving cars. But it gets complicated. It gets so complicated. And he's going to go through examples. But I think what his main point was with showing this, he's saying, look, yeah, they trained some neural networks, but they had so much code that was manual that was telling the car how to drive. But now he's saying, look, they are at Tesla, they are increasingly replacing this 1.0 code, meaning this manually coded logic, with stuff that has been trained end to end. And one thing I was saying last time was this is like this is an old video. This is a very ahead of its time. This is 2018. And so then Tesla has done way more end-to-end training. And self-driving used to not be very good, to be completely honest. At this time, it wasn't very good. He was making good progress while he was there, but it wasn't good. A lot of people have a bad conception of Tesla self-driving. But if you try it today, it's very, very, very good. And I'm not going to pull up this clip. I'm a big fan of George Hotz, but he was talking years ago about how he thought that Tesla was going to eventually go 100% end-to-end. And he was right, I think. I think he was right. I mean, we can double check on that, but this is the way that everyone has gone. Basically, you have a lot of data, you have a lot of compute, and you just are not writing this stuff yourself about if it's a speed limit, then go slower. If it's above the speed limit, then go slower. If this and that, like, you're not doing that kind of stuff. You're letting the neural network search for the perfect driving recipe. And so this, I mean, in hindsight, this talk was this is absolutely the way that Tesla ended up going. Tesla ended up succeeding, and he was laying it out right here. So this is a very prescient talk by Andrej Karpathy. So, okay. He's giving an example here. Like, look at the kind of logic you would have to, with parked cars, like, look, what kind of logic would you need to like detect if a car is parked? It's actually really hard. Like, he's saying, okay, well, you want to see if there's a bounding box around the car. Like, let's just show his example. Like, see, there are these boxes here? Like, where is it? Like, what's the location? Like, this is hard. How do you detect if this is moving or parked? It's very difficult. Or if it's just stopped but not parked. Like, there's a lot of things that you would go into in this logic, and you really you need the neural network to parse this apart, because there's no way you can decompose the problem and really write sound logic that can actually detect this. So now he's talking about he's saying, if the optimization is doing the coding, what are the humans doing? And basically he's saying, so first of all, I think this is outdated. I don't think that necessarily people are doing that much labeling these days, because I think the AI is able to even abstract the labeling away from people. Because just with enough footage, it very well may be able to just infer that's a stop sign, that's a license plate, that's another car, that's a truck, that's whatever, right? All these things I think can be, like, you don't need to label different parts of the video to tell the AI where things are. I think that maybe you do. I don't know. I don't know that for sure, but I think probably at the time that he was doing this, there was a lot more labeling needed, and now there's a lot less. That's my assumption. But what he's saying, basically, like let's just take away the specifics of what he's saying here. He's saying that essentially they are just concerned with getting a good data set. And just with the data set and having the compute, that's what the humans are focused on. And yeah, you set up the neural network architecture and press the train button or whatever, but there's still a lot to do. But what the work becomes is this meta process where you're working on the system that facilitates the optimization to occur. You're not doing the optimization yourself. So he's just kind of talking about what people are doing. So they have just a whole operation for taking data, taking footage from cars, labeling it, turning it into a high quality data set so that they can just throw a ton of compute at it and teach the car to drive itself. Yeah, and he's basically here. He's just saying the most important piece is the data set. It's more important than any theory about machine learning. And yeah, he's saying it, and it can. He basically here he's saying it's hard to label data. Like he's showing all these challenging examples. They're very funny about how hard it is to label data. So even labeling data is hard. And yeah, I'm just trying to go through this. Yeah, there's all these variations. There's different things you wouldn't expect. It's just, even that's hard. And you have to kind of, I guess this is where we left off last time. So lesson 3 is where we left off last time. So basically he was saying all the data is hard. Okay, so we're here where we left off last time. This has been a pretty long stream. And I really do want to talk about the crypto tie-in to all of this. So since we covered a lot of good stuff today, I think this stream went a lot better than last time. I want to end it for today and do another one that actually finishes this video now that we've properly covered this background information. I want to actually finish this video and then I want to tie this into crypto in the next part. And so, yeah, thank you for watching. You can subscribe to me on X or YouTube. My handle is LZRS And yeah, thank you so much. I probably will resume on Monday streaming, but maybe tomorrow, maybe something else. We'll see.